Good morning or good afternoon, I'm not sure about it. My name is Rita Dantas and I'm going to present you the work entitled Multiaxial Fatigue Assessment of S355 steel in the high cycle region by using Susmel's criterion. So, first of all, I would like to present you the main contents and topics of this presentation. I will start by introducing you the motivation and main goals of this work. After that, I'm going to explain you the Susmel's model and present you the experimental fatigue data that will be analyzed and where will be applied multi-axial fatigue model in order to evaluate it. And after that, finally, we are going to conclude about the accuracy of this model. So, as you probably noticed yet, the main topic of this presentation is the multi-axial fatigue that is present in many engineering structures and applications such as wind turbines, as you can see here in this figure 1, and but also in offshore structures and bridges, for example. And around the middle of the 20th century, some models and approaches were developed. It was a couple of years after the presentation and identification for the first time of the phenomenon of fatigue. So probably the first model about multi-axial fatigue was the Gold and Pollard model. After that, a couple of years later, around 1950, appeared the Findlay's model that continues to be wide used and popular, as well as the Sins and Matak models. But earlier, new modern uh, models appeared and were developed as Deng multi-scale approach, which appeared around the 90s, and Podopoulos and Carpenter-Spinelli model, which are also important models to mention. And earlier, around 2000s, the Susmel's model that will be presented throughout this work. So, as you can guess, the main goals of this work are to review and describe Susmel's model, as well as evaluate the accuracy of this model and to assess the fatigue behavior of S355 steel in the high cycle region through this model. And it's important to mention that we'll only be evaluate proportional loadings with constant amplitude. And at the final goal is to determine the fatigue design curves in order to evaluate the fatigue of this material. So, Susmel's model is a critical plan approach, which means that it defines a plan where the probability of crack initiation is higher and where the fatigue damage will be higher. This model defines that this plan is the plan that experiences the maximum shear stress amplitude, and it summarizes the fatigue damage in a singular modified diagram where you can see the different curves here, and as you can see, each one of the curves is defined by other two variables: the negative inverse slope and the shear stress, the reference shear stress that is defined in here, as you can see, at a reference and established number of cycles to failure. And as you can see, for each curve there are a different ratio. This ratio, that is the effective value of the critical plan stress ratio, it's defined like that. And as you can see here, this the stress ratio is calculated based on the normal and shear stress. So it depends on the loading scenario. So, and this also depends on this index M, as you can see here, is calculated through this equation, which implies and requires three different endurance limits. Here you can see the endurance limit for the fully reversed torsional loading. Here the fully reversed axial loading, and finally here is another third fully another endurance limit that has to be larger. It has to have a stress ratio larger than -1. So after that, with this stress ratio, we can calculate the different values of inverse negative slope and the reference amplitude shear stress. Because as you can see here, these variables are defined by a linear equation, a linear function, which depends on this variable. So we can now look at this equation, which defines each one of the curves here. And as you can see here, depends not only on these two variables that I mentioned before, and this pair of variables will originate a different design curve for each loading scenario, but also in this number of cycles. It's a reference number of cycles, which is defined, and usually it is around 2 millions, and it will be taken as it in the. So now looking at these equations, we need to calculate these variables here. So this is possible through these two equations that come from the values of this stress ratio for the condition of fully reversed axial loading and fully reversed torsional loading. As you can see here, we consider this. For this case, this stress ratio, for this case, torsional case, stress ratio is always equal to 0, and for axial case, it's always equal to unit. So now we can rewrite this equation as that, as you can see here. But it's also important to define this value here, that is a limit value for this stress ratio, this effective value, which has to be defined because for some large values of stress ratio, this model tends to be too much conservative, and we want to avoid that. So now looking at the experimental fatigue data that we are going to analyze, we consider 5 different loading conditions, the fully torsional, the fully axial, but also the axial condition with a stress ratio equal to 0.01, and for proportional loading, which is the combination of axial and torsional, we performed these fatigue tests were performed for 0.01 and -1. And it's important to mention that besides being tested under constant amplitude loading, during these tests, the normal stress was defined as half of the shear stress. So here we have mechanical properties of this material, a microstructure that was taken, and also a specimen where these fatigue tests were performed. So now starting to apply Susmel model. As I mentioned before, this equation defines each curve of the modified Euler diagram. So now as a first step, we decide to rewrite this equation as this way. similar to a Baskin law. So you can see here you have, as mentioned before, the same variables that we need to calculate: the reference shear stress, and the inverse slope that was calibrated considering the fatigue data of fully torsional loading and fully axial loading, and we obtain these curves. These curves defines each one of the variables, and in order to calculate that, we needed to calculate this effective stress ratio. So here you can see the values that we obtained based on the value of M index that we calculated as equal to 0.31 based on that equation that I showed before. So it's only necessary to define one thing, that is the reference number of cycles that I said before, that would be 2 millionths. So next step, we defined each one of the design curves. As you can see here, we have the equations for each kind of loading, and here we plot each one of the curves. So it's curious because besides the points collapse around the curve, as you can see here and here, it's quite good. We achieve quite good results. Besides that, as I didn't mention before, but usually stress ratios increases in this direction, and this is verified in this modified diagram. Here we have this line. This curve is the curve of, as you can see, you can see in the legend, is the curve of the fully torsional loading, and as you can see here is the upper curve, and here above we have the curve of axial loading with a stress ratio of 0.01, and I'm not sure if you noticed, but the value was, the largest one was 1.32. So as you can see, evaluating this diagram, the results are good, but we decided to quantify it to see how good is that. So we calculated the error index that was calculated based on this equation, and after that we plotted the results in this frequency histogram, and as you can see, and also we consider that the error index calculated for each specimen could be treated as a random variable following a normal distribution with a half probability density, that is here in this axis, characterized by a mean and a standard deviation. As you can see here, the mean value is quite good, and also the standard deviation, as most part of the results are between the -5% and 5%, which is quite good. But we also decided to plot here this diagram, which plots the calculated number of cycles as function of experimental number of cycles, and as you can see here, the curves, the most part of the numbers, the points are between the factor 5 and 2 curves, as you can see here, factor 5 curves, and this one is the factor 2. So after this, we can conclude that the Susmel model allow us to modulate and assess multiaxial high cycle fatigue in S355 still with a good accuracy, and we determined the fatigue design curves according to this model, which we think that are curves that can represent quite good fatigue behavior for each of the loadings, even the multi-axial loading on this steel, and we determine these curves with error indexes values quite low, around 0% and 5%, what is quite good. And as future works, we'd like to perform additional fatigue tests and extend this work to alternating amplitudes and perform a probabilistic analysis and determine the corresponding design.